Good evening and welcome everybody to N-Simplex Pachinko. This is Obi-Wan Pez. Working on some math tonight. We got by request. Killer King, if you're out there, let me know when you get in. So it's suggested that we work on Epsilon-Delta Proofs, specifically to look at like some of the different ones that are not given every single time you're doing a, the same kind of ones that you're given every single time that you're doing stuff in Calc 1. So, right, yet again, did not plug in the stuff. Again, someday. Righto. Alright, so, heading over to, I gotta get my math stuff. Someday I'll figure it out. I really hope I wasn't muted that whole time. I'm pretty sure I clicked it. Alright, well, just in case I was, this is Obi-Wan Pez for N-Simplex Pachinko. We're going to be doing Epsilon-Delta Proofs tonight, by request. So this came from Killer King. So we're looking at, in the case of Epsilon-Delta Proofs, what we're trying to say here is that if we have some limit that we know should exist, so the limit as x approaches, the one that they always give in the calc classes, right? If limit as x approaches 2 of 3x minus 1 is going to be equal to, well, let's see, that's going to be 3 times 2 is 6, minus 1 is 5. Let's not do if quite yet. So, let's say, given that the limit as x approaches 2 of 3x minus 1 is 5, and we want to prove you know what, let's just start with prove. I'm not a formal mathematician. I'm not super great at a lot of this little random stuff like this, but you want me to teach something? Okay. So we're going to prove that the limit as x approaches 2 of 3x minus 1 is 5. What does that really mean? Well, in terms of calculus, in terms of what Newton and Leibniz had come up with way back in the 1700s, what we're really saying is that we get infinitesimally close to x equals 2, or an x value of 2, then our y value, or the function value in this case, our f of... that's not really... right, f of x becomes infinitesimally close to 5. Now we can relate a lot of this to some of the stuff I had been talking about earlier, much earlier probably, about how we can talk about things being a certain distance apart from each other. So the distance and the difference of two numbers are going to be the same thing. So if we are a certain distance away from something, then the difference between that number and our number is going to be the distance that they are apart. So when we see stuff like x minus a, this really says that... No, hang on. Back up. Absolute value x minus a is equal to some... let's just call it m. Right, this is saying that the distance between x and a is m. Now in this particular case, we know that m has to be a positive value, can be equal to 0 potentially, but has to be non-negative at the very least. So by the way that we define absolute value of x minus a is a piecewise function that says we're going to take x minus a if x is greater than or equal to a, and also a minus x when x is less than a. Or we can shift that around if we want to make the thing you're probably more used to, negative parentheses x minus a. So we can replace a minus x with a negative parentheses x minus a if we feel like it. This is also, again, how I talked about solving absolute value equations and inequalities, and how we really want to focus on, like, what does this stuff actually mean? How can we make it a little more transparent to people who may not be completely on board and understand how this all works? Okay. So we can use this definition, and in fact we don't even need the definition. We could just say we'll just use the distance definition in our phrasing here. So we're going to get infinitesimally close to x equals 2. So that means that the distance between x and 2 in this particular case is going to be really, really tiny. So it will be smaller than some number. We call that number delta. So delta is some arbitrarily small constant value, and if this is true, if we are getting extremely close to 2 with our value of x, then we also need this has to imply that the distance between our function value and 5 has to be less than some other arbitrarily small constant value, which we call epsilon, being the next letter in the Greek alphabet. Do you see where this is going? And this is kind of how they did constants back in the days. They were just like, let's just name it the next letter that we have available. That is, in fact, why pi is the letter pi. Has nothing to do with cakes or pies or anything like that. It has to do with the fact that they had just used, or I think it was Euler, had just used omicron to describe some other constant, and the next one was pi, so he just started using it. Alright, and arbitrarily. Small constant value. Now, it could be that epsilon and delta are the same thing. It could be that they're separated apart from each other. They could be smaller or larger than each other. It doesn't really matter. They have to have some sort of relationship. It's our job to discover what it is. Okay, and then because of that, we have to show, again, that if this is true, that this is also true. Now, there's a little bit of a problem here. I don't know really how to build f of x minus 5 out of x minus 2. Now, it's not difficult in this particular case because it's a linear function. And this is why you've been tasked to do this sort of thing in Calc 1, where you're saying, okay, I have to magically come up with this value over here, f of x minus 5, from our x minus 2. Well, sort of. So one of the things that we could do in this particular case, because again, it's actually pretty easy to just go forward. We could, and this is not how we do things in Epsilon-Delta Proofs, but what your teachers are trying to get you to do is not exactly what you need to do every single time. It's just a convenient way to work on stuff that's harder. It's actually super easy to do this particular one just forward, and that's it. Write the proof. Because you can kind of guess what's going to happen. So with this, we're saying, okay, we've got something that says x minus 2. It's distance between x and 2 is less than delta. All right, we need absolute value 3x minus 1 minus 5 is less than epsilon. Again, it should not be hard to see that's in there. Right? This x minus 2, you can actually literally see it right there. It's 3x minus 6. So that is a 3 times the quantity, x minus 2. So again, super easy to see it. You could, in fact, say, tell you what, I'm going to multiply both sides by 3. And on this step, I'm going to multiply my 3 into the absolute value, which is legal because the absolute value of 3 is equal to 3 right? The absolute value of 3 is equal to 3. And now when you have two absolute values that are multiplied together, this is a rule from absolute value type stuff. Absolute value of x times absolute value of y is equal to the absolute value of their product, xy. So here, this is going to be multiplied in. Its absolute value of 3 times the quantity x minus 2 is less than 3 delta. Multiply this through. Absolute value 3x minus 6 is less than 3 delta. Delta, yep. And then this is going to be the absolute value of 3x minus 1 minus 5 is less than 3 delta, which says that the absolute value of f of x minus 5 is less than 3 delta, which can be equal to some epsilon, some tiny value. So now this is the proof. Now with a linear function, sure, you can go forward like this and just do it. But here's the thing. You really should get practice on how to find this relationship first. Because again, not all functions are this easy where you can just magic up the formula almost ad nihilo in order to come up with f of x minus your limit value L being less than some epsilon. So, by way of contrast, if we want to do this with the limit as x approaches 2 of, let's say, 2x squared plus 7x minus 10. No idea what this is going to be. In fact, this is probably... Yeah, let's make that a minus 7x. Nope, nope, nope. So minus 14 plus 8. It doesn't really matter what I do here. I'm just trying to pick numbers that are not going to be humongous. So 3. Alright, that's not a 0 to this particular function, so I'm pretty happy with it. It's also not the vertex, so this is just a random point on a random parabola. I'm trying to engineer it a little bit so it's not completely disgusting, or too easy, or, again, that it's not a major feature on this particular parabola. So the zeros of this parabola are going to be positive 6, positive 1. So this 2 here is going to get us 4 times 2 is 8, minus 14. 8 minus 14, come on, negative 6 plus 3 is 3. Alright, now you can see how mathematicians struggle with simple math. Alright, if there is anybody out there who does have a question, feel free to pop that in chat, and I will get to you, fairly soon. Or just, hi, how you doing? So here, if we know that this is the limit, so again, plug in 2. You got 2 squared is 4, times 2 is 8, plus 3 is 11, minus 14, 2 times negative 7, is going to be, negative 3. Wow. I'm glad I did that. Hey. Alright, so it's equal to negative 3. I even said before that the zeros were going to be positive 1 and positive 6, so this was going to be in the negative region. It's been a day. I mean, really, it's been a long time. Alright, so anyway, we're going to insist that this is true, and now we have to prove that this limit is actually true. So again, this is not a particularly interesting point for this particular parabola. So we say that, all right, we know that, again, the absolute value, the distance between x and 2, needs to be less than some delta value, some arbitrary constant. And again, this needs to imply that the absolute value between our function and its limit value has to be less than some epsilon, which again is f of x minus a negative 3. Well, f of x, again, is 2x squared minus 7x plus 3 minus a negative 3. That needs to be less than epsilon. Now you can already see that I'm starting kind of naturally at the wrong end of the implication here. This is the wrong end of the proof. You have to show that from the top we get the bottom. But I'm trying to show now from the bottom we can get the top. So again, this is just sort of a natural progression because this side is complicated. It can break down. It can start becoming something easier. So let's try to make it easier. So we've got here the absolute value of 2x squared minus 7x. Here's a plus 3, and this is also a plus 3. So this is going to be plus 6. It's less than epsilon. Okay. Now, interestingly enough, if we try to factor this, this should... I say should. Yeah, not so much. All right. Cool. Now, there's something that's going to happen here, which is going to be interesting. So if we try to factor this, we're trying to get 12 with same factor, or same sign, and the larger factor is negative. So they have the same sign, so they're both going to be negative. We need to add up to negative 7 from a from two factors of 12. So we know that this is going to be negative 3x, negative 4x, plus 6, plus an epsilon, and plus a 2x squared at the front. Okay, first group here is going to be a common factor of x with 2x minus 3. And over here, we've got a common factor of negative 2. So that leaves behind a 2x minus 3. Something just popped out, which is nice. Alright, if you look at it, we've already got an x minus 2 in here, which is what we needed from the beginning. So we go through this and it says absolute value of 2x minus 3 times x minus 2 is less than epsilon. Now, at an x value of 2, or immediately surrounding x equals 2, here, this is going to be 2 times 2 is 4, minus 3 is 1. So we're going to get a value that is infinitesimally close to 1 as we start closing in on x equals 2 from either side on this limit. So this is a positive value. As we take this out, because again, now we can separate these two things. We've got absolute value 2x minus 3 times absolute value x minus 2 is less than epsilon. We've got x minus 2 here, which is what we wanted all the way at the beginning. So now we divide both sides by 2x minus 3 absolute value still. And this thing, the absolute value of 2x minus 3, especially immediately surrounding immediately surrounding x equals 2, but because it's inside the absolute value anyway, it's always going to be positive. We don't technically need it, because again, since it is going to be positive around x equals 2, we could just say, alright, we can divide by that thing because it's going to be positive. If it were negative, it would switch our signs, and that's a problem, at least for this. So here, this divides out this stuff. Now the absolute value of x minus 2 must be less than some epsilon divided by the absolute value of 2x minus 3. That's a cut, well, okay. Again, absolute value 2x minus 3 is immediately surrounding 1, which is going to get us a value of epsilon, or at least be really, really close to a value of epsilon. And in fact, we could just have this, that's fine. So that can be equal to delta. That could be your delta. Why not, right? Or if you want to, epsilon is going to be equal to delta times absolute value 2x minus 3. So, up to you. Alright, so this way, right? When you're going this way, determine the relationship between epsilon and delta. Figure it out. What's it going to be? And then, when you go this way, this is your formal proof. Earlier, when we did this, all we did was the formal proof. Why? Because it was a super easy formula. It was a super easy equation that we were working with. This function, right, we could just say, okay, well, look, x minus 2 is in the thing. But, you know, one of the easiest things to do is to plug in the stuff into both sides of this formula. I shouldn't say formula, right, but kind of is. Plug it into both sides here. X minus 2 is less than delta, and f of x minus 5 is less than epsilon, absolute value on both of them. And then you say, okay, looking at the form that these take, again, we have absolute value x minus 2 is less than delta. We need absolute value 3x minus 1 minus 5 is less than epsilon. So again, on this side, our determining the relationship was kind of superfluous because all we were doing was saying, okay, well, if this is going to be 3x minus 6, it's less than epsilon, this is going to be absolute value of 3 times x minus 2, it's less than epsilon. So here, this is going to be absolute value of 3 times the absolute value of x minus 2, it's less than epsilon, and then divide here. Absolute value of 3 is just 3, so absolute value of x minus 2 is less than epsilon over 3. So epsilon over 3 is our delta. Which again, we figured that out over here. Right? Or epsilon equals 3 delta. Which again is what we found. So again here, determine that relationship between epsilon and delta. Then do your formal proof. And again, in the case of something super easy like a linear form, you don't need to do it, but I would recommend it. Not for your sake, for the sake of understanding how to communicate effectively. Because again, you're not going to need it for this. You're going to need it for this. or worse. For instance, right, if our f of x is equal to, you know what, let's just make a g now because it's not super important, but g of x is equal to the square root of 3x plus 7. Not particularly nice. Okay, and then we want to take the limit at x going to, let's say, negative... well, let's do just negative 1 of g of x is equal to, in this case, our L value, what we call L, is going to be... This isn't going to be nice, is it? That was a mistake. Oh no, actually, it works out. Just because I wasn't paying attention. Plug in negative 1, you get 3 times negative 1 is negative 3, plus 7 is 4. Have square root of 4 is 2. So, yes. Hooray for not paying attention and getting it right anyway. Okay. So limit x goes to negative 1 of g of x is 2. And now we need to prove that. Again, just showing that it works, you can plug in negative 1 and get 2 is not a proof. That is a demonstration. So we can demonstrate that this is true, at least that value is that value. But again, this is not for this. That's not the point. Right? This is not our point. We're not trying to do this right here, right now. We're trying to do something worse later. So again, you could start with the absolute value of x minus negative 1 being less than delta, come up with some relationship between delta and epsilon, and then just make this work. Good luck. Right? Generally speaking, that's not going to work out very nicely. So we need something where we get the square root of 3x plus 7 minus 2 to be less than some arbitrary epsilon. Again, not easy. This time it's going to be much harder. So if you can come up with it, great, good job. I'm not going to accept it. Unless you literally did this one on your homework, and then you're just like, I remember that. But I'm not going to do that if I'm making the exam. I'm going to know what I'm doing. Most of the time. So, where I'm going to start is, again, that's not minus, though. It's find the epsilon-delta relationship. So again, the way we start this is we say, okay, we know that the absolute value of the square root of 3x plus 7 minus 2 is going to be less than some arbitrary epsilon. Now, we need to show that we're going to be able to get something useful out of this. So, here's the thing. This is even a hard starting point for a lot of students, even after they've seen it. Here, what we need to do is we need to multiply by something that's going to get rid of that square root and make it look more like this. So x minus something. So, the best way to do that is going to be multiply by the absolute value, because we need to make sure that this thing is positive so it doesn't mess with the inequality. So multiply by absolute value of the conjugate of this thing. So the conjugate is the square root of 3x plus 7 plus 2. So how does this work? Well, again, we have absolute values, which are ensuring that the thing on the inside is going to be positive. But then we also can take any two absolute values that we are multiplying together and take their product of the insides. And as long as the whole thing is in an absolute value, then we end up with the same thing. Here we got 3x plus 7 plus 2. Oops, no, not that. The other one. Times square root 3x plus 7 minus 2. It's less than. In this case, we've got our epsilon times the absolute value of the square root of 3x plus 7 plus 2. All right, as x starts getting close to positive 1 or negative 1, this value again starts approaching 2, and then we get 2 plus 2 is approximately 4. Now we're not going to change it over, but we just want to keep that in mind, that epsilon appears to be at the moment about 4 times bigger than it was before. Not super important, just, you know. All right, so when we're multiplying these together, again, you're just going to do the whole FOIL thing, but this is also the difference of two squares. So we're going to get the first times the first, the last times the last, and then the first times the last, and the two inners multiplied together are going to cause us to get a positive and a negative 2 square roots of 3x plus 7. So that's gone. It's 0. So we end up with parentheses 3x, the square root of 3x plus 7 squared. So it's just 3x plus 7. Then we end up with negative 2 times positive 2. I was totally pointing to the right one, which is going to be negative 4. Is less than the same stuff we had up above, so I'm not going to recopy it. Over here, we get an absolute value of 3x plus 3. We get the absolute value of 3 times x plus 1. And now it's all fallen together. Absolute value of 3 times the absolute value of x plus 1. And now this is the absolute value of x minus negative 1, or just x plus 1 if you want to keep it that way. That's fine too. Is less than all of this stuff from above. Epsilon times the absolute value of square root of 3x plus 7 plus 2 all over 3. So there's your delta. Pretty, huh? It has a value that is approaching 4, and so 4. And so our epsilon and our delta are off by a factor of approximately 4/3. It's also possible that you can just choose something and say, okay, look, this is what happens in order for us to be just less than that delta. So, this means that we can let this right-hand side become bigger than the value we want. And so we could choose an arbitrary constant. Say that the, all that square root stuff was 5. If we did that, I'm not sure that we get exactly what we want, but well, let's see real quick. So just by doing a thought experiment, if we said that delta was going to be 5/3 epsilon, then we would be able to work this backward and say that that 5 is going to be greater than the actual thing that we've got here, the square root term plus 2. In which case, the square root term, okay, yeah. So the square root term will be less than that 5 epsilon over 3. Once we start walking it back. Okay, so we've got our relationship between epsilon and delta. Some people insist that you do need to pick like a certain value to make this work. I don't think I really care all that much. Although somebody might come around and say, you're absolutely wrong and you have to pick one, so I challenge you. Alright, so then we have to do the formal proof. Which says that we are given some distance between x and -1. It's going to be less than some arbitrary value delta. Right, so if you're doing, yeah, okay. So if you're doing the you have to pick a number thing, you can always say that this delta that we want up here will be less than, oops, 5/3 epsilon, and just go with it. Because again, we picked a number that was just larger. It works. But anyway, we're not doing that right now. So we're not gonna put the epsilon in. We're going to say that given that this is true, we then want to show that we've got all this stuff going on up there. So we're going to say I'm going to multiply both sides by 3. X plus 1 is less than 3 times delta. This is then going to allow me to make this 3 times x plus 1 on the inside of the absolute value. It's less than 3 delta, because again, absolute value of 3 is just 3. Absolute value of 3x plus 3 is less than 3 delta. Again, here, this is the absolute value of 3x plus 7 minus 4. Is less than 3 delta. Now we can go one of two ways with this. One is you can factor. So if we factor this, we're going to factor it as the sum of, or difference of two. Yeah, difference of two squares. So this is going to be the absolute value of, parentheses, square root 3x plus 7 plus 2 times the square root of 3x plus 7 minus 2, which is less than 3 delta. Again, we haven't changed anything. Nothing's getting altered here. It's just the same as it was before. It's just, again, coming at it from a different angle because we weren't inspired, if you will, to figure out how to make all these steps to get the actual function that we need. Here, this thing. So we got to figure out how to get that. So we do the figure out the relationship bit first, then reverse it when we do the formal proof. So it's going to be the absolute value of square root of 3x plus 7 plus 2 times the absolute value of the square root of 3x plus 7 minus 2 is less than 3 delta. Then we say here that this thing is not part of the function, so we're going to divide it off. So divide it off over here, you just get ones. And then over here, this is going to, again, create this square root of 3x plus 7 minus 2 is less than 3 times delta over square root, absolute value square root, 3x plus 7 plus 2. Which is, again, less than 3 times delta over, again, 5, oh, wait a minute, hang on. Hang on. That's backwards. Alright, sure. So let's make it 4. Whew. Bertram! Oh no, what's going on? Good evening and welcome back, as always. It kind of depends. So, like, if it's part of your major, you're going to have to go back and take it again and get better than a C. At least in most programs, you need a C or better as part of all your major classes. If it's not part of your major, or a minor, I suppose, if it's just a, like, I guess if it's an elective, usually you just need a D. And if it's a, like, general education elective, there's maybe some wiggle room there for C or D. But either way, you're probably going to have to take it again. Not particularly. I had to almost redo an entire semester. So I had, at least in the United States, I almost had to redo an entire semester. So it was 6 credits that I had to just literally retake. And I switched one of my classes from one gen ed to another. Almost. I had mono. So it was not a good time. I know, and look at me now, right? Yeah, so I ended up getting ended up failing one class, withdrawing from another. I got a D in a 6-credit class, which was a combination of 3 different classes all in one, which, yeah, it was rough. And I got a pass in a pass-fail class. So I didn't have to take the pass-fail class again. That was off my plate. I had to redo the F, obviously. Oh well, that was part of my major, so I definitely had to do that. I had to retake the 1 semester of the 2-semester progression of this class that I got a D in. Because first semester I got a B, and then I got a D, and it's like, just ouch. All told, when I was done, now keep in mind, I was in state. This was 20 some odd years ago, and I had a pretty decent number of like grants and stuff like that for my freshman year, at least. And my parents were not especially wealthy. It ended up costing me in total. Well, okay. Because they also, yeah, sort of middle. So my dad came from a, very blue-collar, working-class family and was like, I am not going to put up with that for my children. And he was just like, gonna work. So, anyway. Yeah, my brother and I turned out really super academic. He was maybe a little bit upset that we didn't take on the some of the blue collar woodworking, plumbing, car maintenance, that sort of stuff that he just like found second nature to him. He was like, "Yeah, come on, let's go change the tire." I'm like, I can change tires, that's not a problem, but I was just not super enthusiastic about that sort of thing when I was a kid. And then nowadays it's kind of like, yeah, I kind of wish I'd learned more like woodworking skills and other working with your hands type stuff, and it would have been nice, but it's just not something I'm super into. And also when I'm done for the day or for the week, I'm just done. I don't wanna have to fix up the entire house. But anyway, yeah, so it cost us a few thousand every probably every semester. It was somewhere between like 1,000 and 3,000, so it wasn't terrible. But still, that's 8 semesters, so that's about 8 to 12,000, give or take. Well, okay, 8. It wasn't quite as high as 20, so it was somewhere between like 4,000 and 12,000 probably. And then I had loans out after that, so I ended up with about 20,000 in loans at the end of it. So again, all told, everything done, it was somewhere between like 24 and 32,000 for 4 years in state, living on campus every semester. And meal plans and all that stuff. We didn't do we didn't do a meal plan in our senior year because we had off-campus housing that was technically part of campus. It's weird. It was like on-campus apartments that were owned by the school. So, yeah, we lived. I wanted to live in a co-ed apartment with my then girlfriend slash fiance, now wife. Here I am fiddling with my ring. Anyway, so yeah, we stayed off campus and bought our own food, which wasn't super inexpensive, but also it cost us less eventually than doing the meal plan. So, so yeah, like I said, somewhere around 8 to 32,000. No, 28 to 32,000, depending on how you're. Hang on, what did I just do? Yeah. Somewhere between 28 and 32,000, which again was not bad for then. If you go to a good school now, you're expecting probably to pay that in like a year. So we're talking like 4 times that. Which is why it's really important. Go out there, go to your financial aid office, talk with them about everything, and see if there are any grants or like scholarships or stuff that you have not applied to but are eligible for. Because if you get paid like $1,000 for, you know, books or whatever, $1,000 is worth your time for filling out the paperwork. So even if you spend like 10 hours filling out paperwork for like, you know, 15, 20, 30 grants, and you only get 2 of them, that's still probably a few $1,000s for 10 hours of work. You just have to research like what you're actually eligible for. So you got to make sure your GPA overall is doing okay. If you got slammed by this semester because of micro, right? Macro. So if you get slammed this semester because of macro, then it's, you know, gonna be a bit hard, but you can climb back out of that hole. It'll be maybe not super easy, but, you know, easy enough if you really focus and... Uh-oh. Yeah. I mean, if you go out there and work on macro, right? I guess technically this isn't necessarily always going to be less than, right? Because that could be... Alright, so with this, if we let delta equal the epsilon that we had from above, that was epsilon times this thing, square root, oops, wow, no, nested, 3x plus 7 plus 2 all over 3, then this ends up being, this thing is less than just epsilon. The absolute value is square root 3x plus 7 minus 2, which was to be proved. Yeah. Whew. Is that like off-campus type job, or I did work study, but I think I limited it to maybe 3 times a week. I might have done it on 5 once. I really loved my work study job. It was great. So I worked in the equipment room at our audiovisual department. And basically, we would grab the equipment, or like we had a inventory system where we would scan out things that needed to go to specific locations on campus at specific times. And then like everybody would grab equipment, head off to wherever they needed to go, set it up, and then make sure it runs, or make sure that the interface works with the professor's equipment. And then head back to either base, where we'd set up the next hour, the next class change, everybody gets in again, or scan more stuff for the next time. And then we'd have the entire time that class was running where we had nothing. And so all of us were just like, all right, homework. Like, scramble, let's do this. It was so great. So, it was a hard, physically demanding job, but at the same time, I mean, it wasn't like super demanding mentally or physically even. But sometimes it'd just be like, I need to get like this TV up these stairs. And so sometimes we'd have like, 2 people go into the same building. You'd lift up the television because it was in this like probably 3-foot by 3-foot box. I mean, it was basically a cube. And the TVs were not small. So you take the TV out of the thing, and usually like put the box. I think we close up the box, turn the brakes on, and then put the TV on top of the box. Most of the time. It was also great the few times that I pulled my back out doing something. Hobbling around campus carrying like two laptops and an LCD projector. And this was, before every room had an LCD projector. This is like, hey, these are expensive pieces of equipment. We have a repository. We don't have like 18 bread. We're doing all right, thanks. How are you? Just recounting one of my work-study jobs at college, which was moving equipment for the audio-visual team. And like I said, this is before, 20-ish years ago, before LCD projectors were in every single room. We had to carry them, or roll them, I guess, with like the laptops and all the other stuff from our equipment room out to the classrooms. So, yeah. Yes. They're still very expensive. There are some miniature ones which are only about 200 to 250, and the bulbs are not quite as horribly expensive as they used to be. But like a good Epson projector would run you $500 for the bulb. So for me, discrete math was mandatory because it was also called math proof. So to do a mathematics major, you had to take math proof, which makes sense, I guess, in that context. And I was also math education, but we had to do the same thing as all the math majors up through sophomore year. So we had to take multivariate calculus, differential equations, and linear algebra. We had to take discrete and 1, 2, 3, 4, There was one or two more. 500 level. Yeah, I don't remember. It's been a long time. That might have been it. In my 500 level, I had to take also a, yeah. I mean, the college bottom, you know, they were perfectly happy to have some of the best equipment, but we had to share it. All right, so one of the things that I have not done yet. And I get the feeling that I'm in danger here if I try to do this. But because I'm going into this blind, which is always a terrible thing to do. If you say we're going to prove limit as n goes to oh, come on, man. You can pull this out. As n goes to -3, or x. What am I doing, n? As x goes to -3 of the function 1 over x plus 3. This is going to get us from the positive side. So on the positive side, this is like -2.9. So -2.9 plus 3, that's going to get us a positive value, so that's going to be positive infinite. Okay, so this becomes a bit harder. And I don't know if I can necessarily prove this just offhand, because it's been a really long time since I've done something like this, but hey, let's try it. So we're going to say that if x starts approaching -3 from the positive side, and becomes infinitesimally close, then our function value for h of x equals 1 over x plus 3, and h of x becomes infinitely large. Ew. No, I did not just draw a triangle. So this is going to be some real easy advice for me to give you, but real hard advice for you to follow. You're going to hate it, and you're not going to want to do it. And you know what I'm going to say. Until you get yourself in a position where you are actually comfortable, spend like 99% of your time not paying attention to your phone, not paying attention to TV, not streaming stuff. Call up people that are in your classes and get your ass into the library. And basically do nothing but study until you feel comfortable. And I guarantee you actually can do this. It's just going to be hard. Because if you get it, if you really get it, and actually like understand what exactly is going on between all these things, it doesn't matter what your previous grades are going to be. You're going to pass the final. You're going to pass the exam. You know, all future exams up until the final. You're going to be able to nail your homework. For me, it took having a fiance who was in the same class. Who was like, no, you're studying with me right now. Like now. Whatever you were playing, no. Just, you're here now. Like, alright? I mean, she still got an A and I got a B in that class, so I still don't know how I pulled off a B in that class. But it was mostly her doing. Yeah, call up everybody you can. Just being like, no, just, you don't have to have anybody, like, you don't have to have a significant other. But call up everybody in those classes who seems even remotely amenable to spending time with you to help you understand stuff. And even if it's like, hey, I'm setting up a study group, would you be interested? And ask like 10 people. And, you know, let's meet for a coffee. Or let's, you know, wherever. You know, let's go to the cafeteria or something like that on, like, you know, this particular day during this time block. You free? After class? Before class? Halfway during, you know, at 9 o'clock at night? Can we just spend, like, an hour getting this all together? If you're serious about it, you can really do it. I know you can. You can do it. You've got this. You just have to take it a lot more seriously. And it's gonna suck. And it's gonna be awful. But I wish that I had listened to that advice. So that's why I'm passing it on to you. Which again, it's gonna suck if you really take my advice and do it, but you're gonna right this ship. It can actually happen. It's just gonna suck. But I mean, these days I do that when I'm like running behind on my paper corrections. So like I'm pretty behind on correcting papers right now. I should probably not stream and just do that. But yeah, you know. I'm in a comfortable position where I still only have, you know, like 100-ish papers that I need to like just get off my desk. It's not that bad because all that is really like 2 per person per class, give or take, maybe 3 or 4, but again, somewhere between there. It's not too bad. I can knock it out in, you know, a few hours. So it's gonna suck, but I can just shove everything aside and say, nope, I am not playing my games, I'm not streaming, I'm not going to do a... Yes. Because keep in mind, it's not 100 term papers or something where I have to read like 5 pages of work. I just have to go through and there's like between 1 and 5 math problems that I already know the answers to and I know what I'm looking for. So I know what grade everybody's going to get within about 3 to 20 seconds of looking at each individual problem. Then I just have to justify it. And say like, you know, you need to do this, you need to do that. And I actually do put in comments. Alright, so. Okay. I mean, if you want to ask a macro question, I can attempt. If it's something more mathy. Can't guarantee anything. My dad was also a pretty strong into business kind of guy. He ended up not having a college degree, but ran like the entire office for this particular company. They were doing customs brokerage on the East Coast. And actually, their clients were like all over the world. Oof. Yeah. That'll do it. Okay. So if x minus -3 is less than delta, so we're still doing the same delta epsilon stuff. This is going to imply, however, that if we have a value that's infinitesimally close to -3, what we're going to do... Oh, no! That formula is also slightly not correct. Or I guess if you're... I guess. There are conditions under which that formula is correct. So what you're doing is a equals p times 1 plus r over n raised to the nt when r over n is the periodic interest rate. Right, and also the n belongs up there. So, reason being that compound interest is just simple interest done multiple times, over and over and over. So I actually just taught this to my other class within the last few weeks. So if you're looking at it, you're saying, okay, A is equal to P plus whatever your interest calculation is going to be. So you can figure out the interest separately, but when you're talking about compound interest, it's actually easier to figure it all out together. So for simple interest, hang on one sec. All right, so here's the easy stuff, right? Simple interest is calculated by taking I equals the principal, so the amount that you have in your account, and you multiply it by your rate, and you multiply that by the amount of time it takes between interest calculations. So like payday loan places will do this, where they have some stupid interest rate, like 500% annual interest, but you only need it for like a week. So read the fine print in your contracts, and goodness, do not get a payday loan, ever, ever, ever. Because again, this is what they do. This is how they make money. They'll charge you an insane, exorbitant amount of interest. But it's only for a short time, so that's how they say, oh, well, we're making money off of it by doing this. Yeah, no kidding. So if you take your particular P and you're saying, you know, whatever that's going to be here, if I take, let's do something like this. So $1,000 times 5% annual interest. So, you know, your 5%. All right, so 5% annual interest for 2 months. So here's the thing. Your units have to agree. That's it. So in this particular case, if we say, okay, this is 5%, this is 5 out of 100, so 5 cents on every dollar, right? 5 cents, 0.05, times 2 months is 2/12 of 1 year. And again, these are approximations because not every month is the same size and all that stuff, but that's close enough. So 1,000 times 5% times 2/12. Now here's the other thing. You don't necessarily have to do it in this order. It could be a different arrangement of units. We could have $1,000 times 0.05/12, which is 5% annual interest rate split amongst each of the 12 months. So your monthly interest rate is 5% over 12. Then the number of months that you are going to be running that calculation is 2 months. So all of this stuff works, you know, relatively based on what your units are. So you can rearrange stuff depending on what your units are. You can call it something slightly different, but it's all the same. It works exactly in the same way. All right, so this is I. Well, if A equals P plus PRT for simple interest, then we got P's here, so we can factor that out. So this is going to be A equals P times 1 plus RT. Now again, this is what you're multiplying by in order to increase P by a certain percentage. So in terms of simple interest, again, simple interest, this is it here. This is a generalized calculation which works for literally anything. It's easiest to do it on simple interest, but we'll let that slide for now. Okay, so what we've got is 1 plus RT is, again, this is the periodic interest rate. So P times R times T will get us, R times T will get us the periodic interest rate. We say again that this is going to be a 0.055% divided by 12 times 2 gets us the amount that that's going to be charged over this small period, which in this case, let me, right, 0.05 over 12 times 2 divided by 6 also is 0.0083333 with repeating 3's. So this here is 0.00833, etc. This is a 0.83 repeated percent interest rate every 2 months. Cool, still there. I was worried I ran right off the page. Okay, so a 0.83% interest rate every 2 months. And again, the 3's are repeated forever. So I'll just keep going. Okay, now what happens with compound interest is that it's not just going to be like that percentage rate over that whole period of time and then that's it. No. What banks like to do is they like to say, okay, look, we're going to give you a monthly rate. Or in this case, it's a bi-monthly rate. Just cuz. So 0.83 repeated percent every 2 months. So if we do a 6-month loan. Okay, so we're going to draw a line here. Let's do a... We're going to come back to that stuff. Hang on. Leave that over there. So we're going to do a 6-month loan. Compounded. Every 2 months. And the annual interest rate is going to be the same, whatever I did up above, 5%. All right, so it's still a 5% annual rate, but it's going to be compounded every 2 months. And we're going to take out that loan for 6 months. So what's going to happen is they're going to take that $1,000. They're going to take the $1,000. They're going to say, over the first 2 months, right, 2 months, the first compounding period, we're going to plug those values in here. So we get A, which we don't know. P is going to be 1,000. Then we get 1 plus R, 0.05, times T is 2/12, which again, we could do 0.05 over 12, then times 2, or whatever it's going to be. This is going to be $1,000 times 1.008333, etc. I mean, pretty much, it's all about profits. So then here, multiply by 1,000, you bump your decimal place over 3. A is going to be equal to $1,008.33. Which again, in this particular case, we're going to just kind of leave off the decimals. Maybe that's dangerous. Yeah, that's kind of dangerous. So we'll just pretend for a moment that these fractions of a cent actually exist. A bank's not going to do that, but we're going to do it for the sake of the calculation. All right, if we take this is our A value. This is how much we owe after the first 2 months. All right, how much do we owe after 4 months? So if we haven't paid anything off, which is a dangerous prospect, we say, okay, this means that this is the first 2 months. And now the next 2 months or total, certainly their pleasure, is going to be A equals. Now, with compounding, what happens is that this value here, our previous A value, becomes the new principal. So $1,008.33 with the repeated bit there, multiplied by, it's going to be the same thing, right? 1 plus 0.05, the 5%, times another 2 months, 2 over 12. So this is also going to be 1.008333, etc. when you multiply those together. Let's store that to R. Okay. So take this number, multiply by R again. So what happens is when we multiply these together, we end up with a new A value. We could say that this is like A sub 2 after 2 months, A sub 4 after 4 months. This is going to be $1,016.73 with 611. I think everything else is ones after here. Something like that. Either way, I'm going to keep the exact values in my calculator and just let it run. So notice here that this is more than like just adding another one of these. Right, if we just added another one, it'd be $1,016.66 with 6's repeated. But it's not, it's going to be 73 cents. So we've made an extra like 7 cents, give or take. Alright, and then if we want to get A6, we're going to do the same thing. So 1,016.73 with 611 on the bottom here. A6 is going to be, take that, multiply it by 1.00833 again. Oops. Okay, and we get $1,025 and 20.8911 cents, you know, multiplied on there at the bottom. This may not exactly be correct because again my calculator might have been rounding in a weird place or something, but yeah, floating point. Okay. 1 plus 0.05 over 12 times 2. That thing. That's not what I wanted. 1,000 times r to the third. There we go. 891. Yeah, that's fine. Close enough. So it's not actually repeated either, but again, whatever. Okay. So A6 is going to be this. If we don't make any payments on this, we're going to owe, after 6 months, $1,025 and 21, probably 21 cents on this. Again, it's an annual rate of 5%, which is eventually going to cost us $50. But because it's compounded, right? If it was a 5% annual rate and it just happened to be compounded or happened to be calculated at the end of the year, then again, that would cost us $50 total. But because it's compounded more often, it's going to cost us more than $50. Not much, but a little bit. Now, the formula for this, you already saw it up there. We're saying that we're taking this 1 plus RT bit, and we're multiplying that over and over and over again. So this is just, really, at the bottom here, A equals 1,000, A6, is equal to 1,000 times 1 plus 0.05 over 12 times 2, because again here we had once every 2 months, raised to the third power, because we're doing it 3 times, right? 1 to get to 2 months, 2 to get to 4 months, and 3 to get to 6 months. So what is this really? Well, again, you saw the formula, but this part here is calculating the periodic interest rate. And this part here is calculating the the number of compounding periods. So, how do we calculate those things when we then kind of standardize what all of our individual constants are going to be? Well, again, R over N is going to be the periodic interest rate. So we get this R over N term, which is telling us that R is the annual interest rate, and N is the number of compounding periods in 1 year. So, realistically, again, we're trying to standardize this. Right? R annual interest rate, and N is the number of compounding periods in 1 year. But it doesn't have to be that, right? This is just a nice way to standardize it. It could be just this. It's just the periodic interest rate. What's the interest rate going to be over the period in which we're doing this thing? So again, this is what we did up here. We said that the interest rate that we're going to get for every 2 months is going to be this 0.833, etc. %. So we get this number, 0.008333, which is going to be added to 1 and then multiplied to all of our numbers over and over and over again. All right, then NT over here is, again, I mean, it's right there in red. I might as well just, is the number of compounding periods. But how do we get that, right? N was the number of compounding periods. In 1 year, and T was the time, but we have to make those units agree. So again, I don't really care what the units are, just as long as this is the number of compounding periods, and this is the, it's written right there, the periodic interest rate. Right? Whatever the period is, it doesn't matter. This is the periodic interest rate. This is the number that you're going to be using as your percentage increase over that block of time, whatever it might be. Right? You want it to be like every 6 days? Sure, let's do that. You know, you want to say like your monthly interest rate is this percentage, and we want to break that down further? Sure, we can do that. It doesn't matter. What is the compounding period? Put that number here. What is the compounding period? Let me rephrase that. What is the compounding period? And then what is the interest rate over that period? Put that rate here. And then up there, put the number of total compounding periods over the entire time, whatever it might be. Again, Standardizing everything is nice, but it isn't necessarily going to be the end-all be-all. So you want to be flexible when it comes to these formulas. Quite frankly, I didn't really examine this too much until last semester when I started teaching this class. I was just like, you always use this formula. But no, you don't need to. If you know what the individual terms are supposed to be, cool, whatever. But if you know what the, like, actual concept is that we're doing, that's the key. That's the key to always getting this right. Even if they throw out some really complicated example. Okay, that's the periodic interest rate. That's the number of periods. What do we have? Let's go. All right. So in this particular case, again, we could have jumped using this formula and said this was $1,000 times 1 plus 0.05 over the number of compounding periods in a year. Right? If it's once every 2 months, there's 6. And then we have up here 6 by the number of years. It's a half. Right? We only wanted to go 6 months. So it's a half of 6, the number of compounding periods in 1 year. So then again, this is 1,000 times 1 plus 0.05 over 6 is going to be the same value we had before. I mean, I know it was going to be, but, you know, I just have to double check, make sure I'm not completely wrong. And then 6, half of that, we get 3. So that's what we did over here. All right, and then we shortcut it. 1,000, $25, and 20 cents with 8912 left over. So realistically, $1,000, $25, and 21 cents. All right, now, Leonhard Euler, we've talked about him many times on this channel. Leonhard Euler went around and he said, wait a sec. Now, if I keep increasing the number of compounding periods, there's some sort of pattern going on here. So he said, let's take A equals, let's pretend for the moment that we're going to charge $1, we're going to loan out $1 at 100% interest, with some unknown number of compounding periods in a year for 1 year. All right, so here he said, let's create a table of values for n, and then here, this 1 plus 1 over n, parentheses raised to the n. What's that going to get us? So just from thinking about it, if n is 1, this means that we're going to only charge interest once at the end of the year. So we're charging 100% interest, which means we're getting $1 back on our dollar. So that's $2. That's it. If we go to n equals 2, what this is going to do is it's going to split our compounding periods into half-year segments. And also, our interest rate is going to get split in half to 50%. So if we charge 50% interest on the first half of the year, that's $1 times 50% is going to get us 50 cents. So now the principal at the half year mark increases to $1.50. And then when we get to the end of the year, that's going to be 50% of $1.50, which is 75 cents. Add that onto the $1.50, it becomes $2.25. All right, if you do it quarterly, so 4 times in a year. Plus 1 over x values ask. Cool. So 1, 2, 4. So if we do this quarterly, we're going to end up with, again, same thing. It's going to drop the periodic interest rate to 1/4 of 100%, so 25% per quarter. So 25% on the first quarter ends up being 25 cents. Excuse me. And then a quarter on the second quarter is going to become 25% of $1.25. So that's going to be more than a quarter. And then it's going to repeat this 4 times through the year. So that's going to get us a total of $2.44 with this partial cent on the end, 140625. Okay, so interesting stuff is happening here. Notice that we increased by 25 cents in the first increase of increasing our n from 1 to 2. Increasing n from 2 to 4, which is a larger gap, on this side increased by less than 25 cents. This is actually, what, like 19? Yeah, 19 cents. For increasing our n value even more than we did the first time. All right, if we go to 12, so how many, we're doing this monthly, so 12 times in a year, it ends up being 2.61 with partial cents, 303,529,02236. And there's more stuff after that, but again, the calculator limits itself to this many decimal places. Notice again, we've increased n quite significantly from 4 to 12 this time, but our value that we've picked up here is only about 17 cents. So that's far less than the 25 cents that we did in the first one, or than the 19 cents we did in the next one. This one's only 17 cents, and yet we increased n significantly. All right, how about 365? So if we do compounding daily, this ends up being 2.7145674820245. Okay, so again, we've picked up basically 10 cents on this next one for increasing our n even more significantly, all the way up to a year's worth where we're doing, we're compounding every single day. So n goes from 12 to 365. That's a big jump. That's like 30 times more. It shouldn't be surprising, right? That's the number of days in a month on average. Yeah, it's not even, but approximately on average, the number of days per month. All right, and Euler decided at this point, like, what if we just divorce ourselves from reality? What happens if we start increasing this value even more and more and more, all the way to n goes to an infinitely large value? So we can't really do that, but we can say, all right, let's just get absurdly large now. Now, at this point, he did not have the, calculation ability to just jump to, let's take a millionth and raise it a million times. Like, nobody has time for that. So there's other, calculus methods to be able to figure this stuff out at higher values. I don't even know what they are, but okay, so 2.7182804693193, and again, continues after that. This is a million. Notice here there's no appreciable difference in the number of, like, cents. And at this point, really, we just kind of divorce ourselves from reality and say, let's just look at this, because now we've got a number that this appears to be approaching. So as n approaches infinity, this value does approach a very specific value. So this is going to approach 2.7182818459045 with many, many more numbers, an infinite number of numbers after this. There's no rational value that this is going to approach. This is an irrational number. It is not only just any irrational number, it is transcendental, and it is called E, also known as Euler's constant. So, given the letter E by somebody as a permanent reminder that this is Euler's number, we can use this value. So Euler found out eventually that the function e to the x is going to be the limit as n goes to infinity of 1 plus x over n to the n. Which also makes it rather interesting to take this particular thing up here and say, what happens if we increase the number of compounding periods in a year to infinity? So we're going to take, it's going to take this basic formula here. Where we're saying, okay, take the limit as n goes to infinity of p times 1 plus r over n raised to the nt. Well, this is the same as p times the limit as n goes to infinity of 1 plus r over n raised to the n, all raised to the t. Because here t is a multiplier in our exponent. So you can take whatever the thing is that it's raising to a power, or whatever it's being multiplied to, you could take that as an inner exponential. So then, when we do this, we say, oh, look, limit as n goes to infinity of 1 plus r over n to the n. That's this formula here, e to the x. But now it's going to be e to the r, because r is in the place of where our x was up here. So this is p times e to the r, parentheses around e to the r, raised to the t. Well, we don't need the parentheses anymore. When you take a power of a power, we can reverse what we did back here and recombine them as multiplication. So p times e to the r times t. That's where we get this thing. So this has an infinite number of compounding periods. So we say it's compounding continuously. This also gets us an upper bound, or a maximum, on compound interest. When P, R, and T are always the same. So if we took our previous thing and we said, all right, we want to find out what happens if we take that $1,000 loan for 6 months. compounded continuously. 5% annual interest. So this is A equals P is 1,000 times E to the R is 0.05% annual. Sorry, 5% annual, so 0.05 is the number. Times 6 months is a half a year. So 1,000 times E to the 0.025. So for 6 months, this is going to be $1,025 and 31 with 5121 partial. At this point, most likely, we're going to round that up. It's not really going to matter all that much. But banks do like to increase profits by saying, well, you know, we'll just round all these partial numbers up. So this is going to be our theoretical maximum for compound interest on this particular loan. So again, $1,000 at 5% annual interest for 6 months. Given that, we had earlier compounded every 2 months was going to get us $1,025.21, and now compounded continuously gets us $1,025.32. Again, not a very appreciable difference, but there's some. Go like that. All right. So I hope that makes sense. And the next question is anyone else here? Does anyone else have any questions? Or any follow-up questions? Because this is kind of a lot, but... So there's also another set of formulas. All these that we were talking about up here were all one-time payments. So you put the money in the bank and you just kind of forget about it. But that's not really how the real world works, right? It's just ridiculous. So, in real life, what generally happens is you make multi-payments. Might be called an annuity. And generally speaking, what you're doing is you're making a payment. So, yeah, it could work. Okay, So you're going to make a first payment, whatever that might be. And then you're going to find out that the amount of interest that this earns is going to be your 1 plus r over n to the nt. Which is going to say, like, your first payment is going to earn this much back at the end. Then, your second payment is going to earn, well, not quite the same amount, but almost. So it's going to be 1 plus r over n raised to the nt minus 1. Because it's going to have one fewer compounding period to accrue interest than the one before it. Now granted, P1 and P2, generally speaking, what we do is we say that those payments are the same, like all the way across the board. Okay, and then P3 likewise is going to be 1 plus r over n to the nt minus 2. I mean, really, these are all the same payment. This is just... This is payment 1 plus interest. Payment 2 plus interest. Payment 3 plus interest. And we continue this on and on. I mean, Megalomorph, you know. Alright, so then we can go out to, like, payment n minus 1. The second to last payment. We're still going to get interest on it. Just not very much. So in this case, we get P times 1 plus r over n raised to the nt minus, in this case, we had always subtracted 1 less than the value down there. So this was going to be nt minus n minus 2, parentheses. Oh no. Alright, then we got, dare I ask? I mean, I do, but you know. This is going to be P times 1 plus r over n raised to the nt minus parentheses n minus 1. So the final payment, P sub n plus interest. Now here's the thing. This works really nicely as a sequence. Oh no. Alright, so the total sum of all this is a geometric sequence. And in a geometric sequence, and it has to be finite. I guess series, because we're summing them all up, is that when we have, again, our initial amount, it's going to be a sub 1. R is going to, not that R. R is going to be the growth factor, or the ratio. Black Demon Fox. Hello. Good morning. Or good evening, I guess. Yes, so go ahead and ask a question. and I will get right to it. I'm explaining some financial stuff, so it's not a super important thing. Uh, this is going beyond the original question. So, the Black Demon Fox, what is your parabolas question for today? All right, R is going to be our growth factor or ratio between the successive individual terms. You're awful. Chemistry work. Okay. Oh, no. This is this is financial calculation. So if you put money in the bank every single, let's say, month or quarter or anything else, then we're trying to work out how much interest you're going to generate inside the bank, letting them borrow your money. Yeah, I can see where you're getting that with the P and R. And N and T. Just missing a V. So the sum of all of those things was going to be equal to a sub 1 times 1 minus r to the n. In this case, it's not actually n, and not little case r. Okay. Over 1 minus r. Okay. So actually, right, ideal gas law with PV equals nRT. This is just the Microsoft whiteboard, but I've kind of altered the background a little bit. And allegedly there's going to be like a new version coming out soon. I've previewed it. It is okay. Changes a few things just a little bit, but so I come over to here to format background and then change it to well, you can see it here. It's graph paper, but I just zoom in really far. All right, I zoom out to 100%. So you're trying to find R. You know goodness. That your pressure was 1, your volume was 1. Nope. Nope. Your volume is 22.4 liters. Let's see. We don't know what R is. N. You have to forgive me on that one. I don't remember what N is. Times R times T is 273, so this is our standard temperature. 0 degrees Kelvin, or 0 degrees Fahrenheit, or, wow, 0 degrees Celsius. So, super easy. It's just 0, right? Of course not. All right, so in this case, we've got our 1 times 22.4, so that's just going to stay where it is. And then R is going to be equal to, if we divide off N and divide off 273. All right, you got your 22.4 over n times 273. Okay, and it's just the number of moles, so cool. So you said 1 mole. Equals 1. We can't use atmospheres, can we? No, it is. Okay, cool. So yeah. I will leave it as an exercise to the reader to figure out what the units on R are, because that's going to be rather interesting for that one. Okay. So a sub 1 is going to be P times 1 plus R over N to the NT times 1 minus R to the K is going to be, again, what is our ratio? So our ratio over all of this is 1 plus R over N to the NT, nope, sorry, to the minus 1. So we're subtracting 1 for the, oh, yeah. There you go. Yep, so 1 plus R to the N to the negative first is going to be how we, oops, not done yet. Yep, no problem. Is going to be our R value. So this is what we're multiplying by every single time. Essentially, we're dividing by 1 plus R over N every single time that we come across. All right, then we figure out how many times is this happening. So our K value here is really, okay, it's the, that's a K here. Ew, well. Yeah, no problem. If you have any more questions, let me know. Okay, so we can do this as like K instead of... So this is K minus 2. And K minus 1. I teach at a 2-year college. And I teach pretty much anything from like basic algebra all the way up through differential equations. So depends on the semester, depends on the school's need. Lately I've been doing pretty much only precalculus and calculus and differential equations, occasional other stuff here and there. These last couple of semesters I've taught finance, or it includes financial math. It's called, no, I'm on the East Coast. Anyway. So this is going to end up being our K value here. K value. It's going to be equal to NT. I mean, I don't know Mission College, but possibly. Let's find out. Mission College in Santa Clara, public 2-year. Sounds about right. I guess another question is like, do you know what the culture of that school is? So, for instance, like, is there a lot of students who go there to just get associates, or are they trying to, like, get boosted into doing a 4-year degree after? Or both? Because that's really what's happening at ours, is there's lots of students here who just want a cheaper option to go to a 4-year school. There are some people who need to boost their GPA before they try to get into a 4-year school. Or, like, you know, develop better study habits, that sort of stuff. But a lot of people, I'd say even possibly a majority of our students, are going to go to a 4-year school to get their degree after they're done with us. After they've decided what they want to do, taken whatever classes they need for the first 2 years. And possibly several more. Okay. So this is going to be, again, this thing raised to the NT. All over 1 minus R, again, is 1 plus R over N to the negative first. Okay, so this is going to be P. The interior here is going to get multiplied by this thing. Now here, this is going to make this one a 1 plus R over N to the NT. This next part is going to be minus. This is 1 over that thing raised to the NT, and this is this thing raised to the NT. So those are exactly the same term. They're just going to divide out. Alright, now, there's something that's not quite right here. I think the bottom is just going to simplify itself to make this work, but it's making me slightly paranoid. Is it -1? I think it might be -1. No, I mean, it should be that number of compounding periods. Sorry. So this is kind of a combination. The formula that I'm actually working out is only taught in my mathematical literacy course, wherein we teach students how to calculate values of annuities. So here you're making like monthly payments into an annuity in order to have a certain amount of money by the end. So for instance, like a retirement account. So this is something that's extremely useful for these particular students. They're not necessarily super great at math, but at the same time, like, they really need this because this is the kind of math that they absolutely need. I'm mixing that with our calculus course, which is going to do series. So, like, finding the sums of all this stuff. But so if I do this, this ends up being the number of times this is done. It's going to be NT minus 1. No, because like the... Alright. I'm just arguing with myself at this point. So for some reason or another, this needs to be a minus 1. I screwed up somewhere. And I mean, it looks like I just screwed up here, that it needs to be that minus 1. So then this would be minus 2, so that this would be minus 3. But at the same time, that's kind of aggravating me, because you should be getting the same number of periods there are. You should be getting all of those interest payments here. Arg. Okay, so let's have this be 1 plus r over n, so the negative first. So if this negative 1 exists here, then we're going to have one spare minus 1 of those. Then we can multiply it down into the denominator. So that's aggravating, but whatever, it'll work. Plus r over n to the first. Here this makes p times the quantity, 1 plus r over n to the nt minus 1. Here this stuff is going to go away. And on the bottom, we get 1 plus r over n to the first, plus that times that is just going to be 1. Minus 1. Which is equal to payment times 1 plus r over n to the nt minus 1 all over. This is going to be 1 minus 1 is 0. So r over n is the only bit that's left. So this is our future value formula. Given multi-payment. So if you end up saving $500 a month at 2% annual interest, compounded also monthly, which, again, they shouldn't really break this. So your units should match. Even if it's quarterly, or even if it's daily, or whatever, it will still work out that way. So, $500 a month at 2% annual interest compounded monthly for 15 years. So in this particular case, A is equal to, our payment is going to be $500 times, parentheses, 1 plus 2% annual interest is 0.02 over 12, raised to the n is 12, t is 15, minus 1, all over 0.02 over 12. Alright, 12 by 15 is 6180. Okay. Being a trig guy, I should know that, but whatever. 500 times. 1.02 over 12. It's going to be 1.00166 with 6 repeated, raised to the 180. Minus 1. All over 0.00166 with those 6's repeating. So if we do this, alright, 500 times 1 plus r raised to the 180 minus 1 divided by r. Alright, this is going to get us 104,000. $104,856 and 52 with partial 7/8, so that's 53 cents. So $500 a month is going to be times 12, $6,000 a year, which, you know, if you have a job, that's a pretty decent amount to be saving. Especially when you first start out. Okay, and then multiplied by 15 years is going to be about $90,000, or it's going to be $90,000 that we put in. So positive $500 per month times 12 months per year. Unit analysis, divide out months times 15 years. Divide out years. So now we just have this, again, 90,000. And years is the only, wait, dollars. Not years. $90,000 over that 15-year period. So this is the amount deposited. So the amount we earned in interest is going to be $104,856.53 minus 90,000. So we end up with a total of $14,856.53 as just interest added. Over 15 years, it's just shy of $1,000 a year. It's not too bad for, you know, not touching that money. Alright, we could do the same thing for loans, but I'm not gonna. The amount you take during the first month is going to start accruing interest. Or, sorry, the amount that you're going to pay off in the last month is going to gain a whole bunch of interest. And so it ends up being essentially this term here. And then when you move over one, it's going to do the same thing as this one. It's, you know, the next payment back from the end is going to end up accruing one fewer month worth of interest, and then so on and so forth, back all the way until you get to the end, where you have 1 month that accrues only 1 month of interest, being your first payment. So that one gets a little bit sticky, which so Bertram, if you're still around, the loan amount is going to end up being P equals, this is your principal, so your principal loan amount is going to be P equals, so this is why we didn't use P for a number of the other things, but M for monthly payment times 1 minus parentheses 1 plus R over N raised to the negative NT all over R over N. Alright, so calculated much the same way, it's just going to use some different terms. So if we had like a $60,000 loan taken at 3.6% interest, annual interest, for 10 years. Alright, so we got 60,000 is equal to M, our payment. We have no idea what that's going to be. It's going to be 1 minus parentheses 1 plus 0.036 over 12, because again, we're going to make monthly payments, minus 12 times 10. R 0.036 over N 12. Alright, M is going to be equal to 60,000 multiplied by this number here. So this is going to divide out and get us a 3,003. 0.003. Okay, this is all multiplied to the other side with the 60,000, and then all this stuff is divided underneath the 60,000. So 1 minus parentheses 1 plus, well, 1.003. Let's just be realistic about it. To the negative 120th power. Okay, we got a total here. Our monthly payment will be $596 and 12 with partial 99, so 13 cents. Woo! Amogus forever. How you doing? If you have any questions, let me know. Or if you want to get us back onto our original topic. Nice. Alright, so this is also something that I tell my students, even when this little partial amount here is like a 1, you actually want to round that up. Because if you round it down to $596.12, your monthly payment, you're going to be paying interest on fractions of cents, which eventually add up. So you're going to want to round up, even if, like I said, the situation would be rounding down is fine. In real calculations, it's not going to be off by that much. You're probably going to have to pay a little bit more on your last payment, just slightly, like a few cents, maybe $1. All depending on the whole situation, of course. In this case, that number is so close to 13 cents anyway that the difference between them is going to be pretty minuscule. Yes. I keep bringing that up and my students just stare at me blankly now. I'm getting old. Yeah, it's Mike Judge movie. Oh, you don't know who Mike Judge is. Okay, cool. Still get a couple who are like, oh yeah, Office Space, I watched that. I was like, okay. My dad likes it. Why? 2 curbs! Ooh. Well, that sounds fun. Are you doing anything particular right now? Like in terms of the... I think you said you don't want to give away too much, but... No, okay. Oh, okay. Yeah, Beavis and Butthead. Okay. I was never really into that particular section, but... Hey, Superbrain. Well, welcome back. So yeah, there's all these like repayment formulas and stuff like that for finding stuff. So Bertram, with you taking macroeconomics, this is probably going to be a part of it at some point. But you don't necessarily have to know every single little detail. Yeah, me too. I'm thinking of going and grabbing a beer from the fridge and rating somebody else. So, see how it goes. Should be fairly short order here, I think. But, endpoints normalized in d-dimensional space. How do you optimize them and push them as far apart as possible? Yeah, okay. Right, that one. Okay. Okay, so... I was talking Epsilon-Delta Proofs at the beginning. Again, this is to go back to Killer King and their discussion with somebody who was like, oh, this is just... calculus is all based on nonsense. Look at this thing. This is BS. Look at that. And They were basically like, this whole determining the relationship between epsilon and delta and then just walking it backwards to them was just nonsense. And so I was like, okay, well, if you do it with a linear function, yeah, it's pretty nonsense because you can literally just do the formal proof part of it without doing a whole lot of work. If you just see the part that you need over here, you can be like, oh look, it's 3x minus 6. That's triple x minus 2. And we can come up with that. Okay, no problem. So you can do the formal proof real quickly when you run through it. But when you start doing stuff like a quadratic, it becomes a little less trivial to do the determining the relationship first and then running the formal proof essentially backwards, which it's not exactly it's not. Did I literally? Yeah, I just left this one where it was. So I said here we can just reverse it and make the formal proof. But when you start looking at a function like this, this becomes much more non-trivial. So here I said, all right, if we're going to do this whole epsilon-delta relationship thing, sure, let's take the conjugate of this particular limit. Well, I mean, it's not a limit, but this particular absolute value. Let's take the conjugate of the stuff that's in here and multiply it on both sides. It's always positive, so our inequality will remain the same. Then when we combine the ones on the left, it collapses to this nice form, which eventually becomes x plus 1. And then on the right, we've got all this other stuff. Delta is equal to epsilon times that conjugate over 3. I guess question for, let's go with Megalomorph, since you probably teach this. Probably. Do you insist that this needs to be a number? And if so, in this particular case, is it a particular number? Okay. So in this particular case, it's equal to... That's fine. So in this particular case, that is actually exactly equal to 4 when x is, whatever I said, negative 1. So it's looking like we want this to be less than 4/3 epsilon. So the problem, I guess, would be if we're approaching negative 1 from one side or the other, it's going to be slightly more, slightly less than 4. So, like, it's going to be right around 4, but it's not necessarily going to be less than that. So I think we'd want to take this and be like 4.8. Or something roughly like that. It's going to be, you know... I mean, literally any other number other than 4 that is slightly larger than 4. So I was originally like, let's just do 5. So then when I plugged it in and went down here, I ran into a bit of a problem because I was like, well, if that thing down here is 5, or if we're approximating it as 5, it's no longer less than because it's on the bottom. But if we let delta be this thing, epsilon, times the conjugate over 3, then it's exactly going to get rid of this stuff. Then we got lost on many tangents. Then I said it's also going to be non-trivial on something like this, where we say, okay, if x is going to be approaching -3 from the positive direction, this value is going to become infinitesimally close to -3, and then h of x is going to become infinitely large. So then this inequality, x minus -3, is going to be less than delta, is going to have to imply, again, what we're trying to prove, is that the absolute value of the function h of x minus our limit value L must be less than. Now in this case, L, we literally can't have it be listed here as infinity. It just doesn't work like that. So then we have to say that the distance between h of x and the limit is going to have to be less than, actually that's not true anymore. We want it to be greater than some particular value n. Or no, is it still less than? Man. We're having a good day. Alright. Cool, cool. Well, I guess we'll find out pretty quick. So, again, we're going to find the relationship. So 1 over x plus 3 minus L. If it's greater than some big value n, I think it is less. Alright, let's do it like that. So the distance between our current function value and infinity is going to be less than some arbitrarily large number in this case. So as we get closer, we're going to start getting closer and closer to infinity. I get the feeling I'm still doing it wrong, but meh. Okay, so if we multiply by x plus 3, oh, and divide by L. So if we multiply by 1 over x plus 3 minus L, multiply both sides by absolute value of x plus 3 over L. Really? I need a triangle there. Okay. This is the... I can't write limit there. We're trying to prove a limit. Oh, man. Alright, so if we multiply that in, that's going to be Mogus. Awesome, thank you. This is going to be 1 over L. Absolute value 1 over L minus, here the L's divide out, and we get an x plus 3 up top. Oh, well, actually, we can pull out a negative here. That's fine. And this is still absolute value x plus 3, which... yeah, that's going to cause a problem, though. So x plus 3 is also approaching 0 as L. Oh, wait, those are big numbers. Okay, so we're essentially getting an infinity times 0. It's also... Cool. Cool. Alright, we're running out of steam here. Damn. Alright, then here, this -1 can be absolute valued on the inside. And then we got x plus 3 minus 1 over L. Less than n over L. Absolute value x plus 3. Alright, so I'm blocking it too. But I'm also doing this wrong. So I gotta look this up and try it again later. But at any rate, let's start taking a look at who we got for tonight. Boss Lady B has new kittens that she's fostering, which are really, really cute. And oh my god, I think I'm gonna explode. Might be worthwhile. Let's see, everybody else. Yeah. All right. So we're gonna go see Boss Lady B and her awesome kittens, who are named Butch Cat City and the Sundance Kit, I think. So, how do you find the area of where two circles intersect? Oh man. So I would say, all right, we'll do this real quick. If you're going to take two circles and intersect them like this, and you want to find the area of this thing, then you are going to want to run this as a polar calculation, or you could turn them on their sides and do something like, I guess we could do this in Y. So if you knew exactly where this was in space, yeah. So you could do it either in polar, or you could do it here in function, but you'd have to turn it sideways. So if these were centered at particular points with, let's say, same radius, just to make it easier, you could also find the ones that are not centered. So here if we had like x squared, nope, x minus x plus 2 squared plus y squared equals 25. And here x minus 3 squared plus y squared equals 25. So I would do this as turning it sideways this way and saying this equation here is 25 minus y squared. Take the square root. We only want the positive side of this particular circle. And then we're going to subtract 2 from that. So it's x equals this minus 2 for that one. And then for this one, this is going to be 25 minus y squared, square rooted, and we want the negative version of this because that's only going to be on this side. And then we're adding 3 to both sides, so 3 minus that. And that's equal to x here. Then you'd want to find the intersection points. I mean, that's slicing a pie, but here you're not, you've got a circular section.